Right now. Yes, thank you. Okay. Hello, everyone. I am Luiz Pool from the Universidade Federal de São Carlos, do Brazil. I'm here to present our work on distributed novelty detection on the edge for IoT network security. Our main motivation was the growth of IoT and associated risks in recent years, such as the record-breaking denial of service attacks from IoT botnets. To address such risks, network intrusion detection systems, especially those detecting anomalies, need to work well in IoT and fog scenarios. To that end, we chose a novelty detection algorithm to be ported in a fog scenario intending to have a small detection latency without quality degradation. Our scenario is a common IoT scenario where sensors at the edge communicate via gateways to the public internet. Traditionally, the risk is at the edges, and the power to detect such risks is in the cloud. We aim to reduce the detection latency by running the system on small fog computers nearest to the data source. Previous work on this subject includes BigFlow, a system that spans from network flow description extraction to alarm generation. However, this system requires external updates and is cloud only. Another inspiring work is Catraca. It also handles flow extraction to alarm generation and, by using network virtualization functions, can run probes in the fog. However, detection is done in the cloud. Another approach is the ICCSA IoT architecture, where 3 novelty detection algorithms are evaluated in a fog and IoT context. However, this architecture does not implement a full system, handling large data. With the state-of-the-art explored, we present the chosen algorithm, MINAS. MINAS is an offline-online novelty detection algorithm that takes a flow of examples and gives examples labeled as known, extension of a known class, novelty, or unknown. To that end, MINAS uses a list of spherical clusters as model and Euclidean distance for the classification task. It also uses k-means and clustering as basis to find new patterns. Our proposal is to employ MINAS in an intrusion detection role in a distributed fog environment, following the ICCSA architecture. We also want to observe the effects on classification quality due to the change from sequential to a distributed algorithm. As for our method, we chose a technique and platform for the distributed implementation, and in the end, we increased the fog usage in the architecture to minimize latency and also due to technology constraints. For validation, our experiments were designed with a suitable environment and data set. Also, metrics were chosen for quality and scalability assertion. Our implementation uses OpenMPI and is architected in 2 modules, root and leaf. One node runs the root module, and the remaining nodes in the cluster run the leaf module. The root module has 2 tasks, sampler and detector, while the leaf has the classifier and model receiver tasks. Following the sequencing diagram, input data is taken in by the sampler and distributed via round robin to each leaf, while the classifier task is run distributed on the leaf nodes. This classifier takes a sample and the current model and assigns a cluster's label. If found, sending the result to the detector. The detector task then takes the labeled samples from the leaves and puts forth this result to the application's output for our next system. The detector task also stores the samples labeled as unknown to execute the novelty detection method when needed, and then broadcasts these new sphere clusters to the model receiver at the leaves. The model receiver is used to maintain the leaf model up to date asynchronously. In our experiments, our setup was a 3 Raspberry Pi 3B cluster over Ethernet on the December 2015 segment of the Kyoto 2006 intrusion detection dataset. This dataset was treated and then split in 10% for training and with only normal class and 90% for the test with majority attack class. We chose this distribution to highlight the novelty detection aspect, as our goal is to detect never seen before attacks. For the quality measurement, we use multi-class confusion matrix with novelty label assignment as its derived matrix. For scalability, we use GNU time measurements as we have a fixed size test dataset. So this is the stream visualization for the reference means implementation and the new development, both in sequential operation. In this visualization, novelties are shown as dashed vertical lines with some labels at the top. Those lines show us that the implementation catches, or new implementation catches less novelties, being 9 instead of the previous 12. In this visualization for each sample in the output stream, the confusion matrix and the derived summary matrix are updated and presented as the horizontal curves. Those curves show us that there is some discrepancy in the implementations, but the observed metrics are roughly the same. For the parallel undistributed versions of the experiment, fewer novelties were detected, but we see no significant change in summary metrics. Again, the main effect we want to draw attention to is the shift for the label 0 from the 300K mark to the 400K mark in the distributed version. This shift was our main concern when developing a synchronous novelty detection task. As the main classifier is still working, the model is updated, and until the proper propagation of the novel clusters, those classifiers are producing results with an incomplete model. It also shows the behavior of the Minas algorithm, where samples used for new clusters are discarded, even if they could be presented with a more accurate label at the cost of duplicated output samples. Finally, this is the summary of our main experiments. The main takeaways here are the speed up, where we had a maximum of 0.97 with 4 nodes and 12 processors. And also the time taken, where the reference implementation took 2,700 seconds and our test took around 100 seconds to handle the same data test. This is the overview of time usage on the root node per added CPU instance. We can see that the user metric and the system metric tend towards each other at 200 seconds as we add instances. We reason that is due to computation versus communication limit in our implementation. In conclusion, data stream novelty detection as in network intrusion detection or even system behavior monitoring and analysis on IoT environments is still challenging due to the data volume, latency, and small device constraints. This approach has some success in handling the intrusion detection in this constraint scenario, while the effects of distributing this algorithm cause an impact on the quality measurements, and mitigation of those impacts must be included in further attempts. Our implementation was faster than the reference one, however, good speedup was not found. Further work can be done with other novelty detection algorithms or by changing Minas internals. Other line of work can be done on improving communication to computation ratio or load balancing. So this is our work, and thank you everyone for listening, and I'm open to questions. Yes? Yes. Actually, no. As the Minas takes only unknown samples, buffers it in a small small segment of memory and then runs the k-means to detect novelties. Thus, it is slow. However, we can control the buffer amount with parameters on the Minas algorithm. So this task here is sequential on one thread only, and thus not distributed. The novelty detection is asynchronous but not distributed in each leaf node or parallel in each node. We had issues. We could use clustering, which is a better algorithm for this case. However, the implementation was not done in clustering. Try other parameters. Let me show you what I'm talking about. On the literature, there is parameters for the Minas algorithm, and we chose some sane parameters. However, we did not do a further optimization to not skew the results towards a better result than it could be. So we try to maintain the reference implementation parameters and the bibliography parameters to the Minas algorithm. One of these parameters is decay for the k-means and the other clustering algorithms to generate novelty, to limit how many novelties can be detected on each run of the novelty detection algorithm. However, as I said before, this is limited here by the buffer amount we can use. Other clustering algorithm is the clustering, which, despite the fact that it can operate in a streaming fashion, that is no key necessary, just a key for the amount of memory used. It was not used in this fashion. The Minas uses it in a batching fashion, not a streaming fashion.